Okay, let's slowly start the lecture. So I'll continue the line that Lorenzo started, and my hope is to convince you by the end of this lecture that this technique is actually the simplest technique to model plasma. It's much easier than magnetohydrodynamics codes, for example. So I hope that by the end of my lecture and listening to Lorenzo's lecture, you can actually just go ahead and code the whole code yourself. So I've seen examples when people just coded the whole code in a week or something. It's much easier than MHD or anything else. So just to remind you how the core of this algorithm looks like. So Lorenzo already described to you which equations we're solving. We're solving Maxwell's equations on the grid with these two constraints. And for each particle, we're solving the momentum advancement at each time step. So the whole loop looks like we start with some particle distribution. We know the initial electromagnetic fields. We know initial particle momentum and position. We can solve this via the Boris algorithm or any other algorithm to get the new moment of the particle. Then we can do this interaction between the particles and the grid just by computing charge densities and the currents from the distribution of the particles. And then we can use them again as source terms in this Maxwell's equations, interpolate the force again, and continue this loop basically indefinitely. So it looks very simple, and it is very simple in practice. So now I'm gonna just go over like this few technical things that Lorenzo highlighted, and I'll just go through sort of deriving how this works numerically. So the first thing that we talked about is how to enforce constraints, which are div B equals to 0 and divergence E equals to the charge density. So almost all PIC codes use what's called an EMASH. So this is something very similar to the constraint transport that you've heard about in MHD. And basically the idea here is that electric and magnetic fields live on different places of your cell. So electric field components live on faces, and magnetic fields lives in sort of centers of the interfaces. And this specific choice allows you to conserve divergence of B if you start from divergence B equals to 0 distribution of fields. It's also true that if you start from something which is not div B equals to 0, it will just keep it going forever. It will not smooth it out. So I'll just illustrate how this works in 2D. So in 2D, this is your cell. Electric field leaves here. This is the electric field component out of the plane. This is the electric field component along y. This is coordinate axis, x, y, z. The bz leaves here. Bx leaves here. Ex leaves here. By leaves here. And I'll call indices of the grid cells with usual ij thingy. So let's compute the time derivative of divergence of B. This is basically what we need to construct in order to ensure that this thing is 0. So divergence of B is nicely defined at the cell center. You have this Bx here and here. You can construct a derivative of that at the cell center, and the same for By. So divergence of B at next time step, let's call it n plus 1, which is defined at I plus half, j plus a half, is Bx n plus a half, I plus 1, j plus a half, minus Bx n plus 1 half, I j plus 1 half, divided by delta x, which is the size of your cell, plus By n plus a half, I plus a half, j plus 1, minus By n plus a half, I plus a half j. This you divide by delta y. So this is your numerical divergence. And then you should just remember the evolution equations for these components bx and by. And in 2D, this is very simple. dbx over dt is just minus dez over dy. For simplicity, sometimes I'll call c equals to 1. So basically, all information about the speed of light is hidden in the time step, in the value of the time step and the value of the cell size. And then dby over dt is dez over dx. Okay? So basically, you can use this leapfrog algorithm that Lorenzo told you about, that basically the time derivative of the b is, to compute that, you use an electric field value at the time between the values, between the times where the magnetic field is defined. So this bx n plus a half minus bx n minus a half divided by delta t is minus electric field divided at n. Let's say it like this. And this is a numerical derivative over y, which we compute at this position. So the ez at this position minus ez at this position gives you the derivative over y, which is defined here, where bx leaves. So this is the beauty of this e-mesh. Basically, by displacing the magnetic and electric field components, you can compute curls with second-order accuracy at the positions where the other field component leaves. And if you'll just plug this here, you get something like Ez at time moment n, ij plus 1 minus Ez ijn minus Ez n I plus 1 j plus 1 plus Ez n I plus 1 j, and then basically the same terms. So this is basically 0 because all those terms cancel out sequentially, like this and this, 0. So I just basically plugged in this equations here and basically assumed that the divergence of the previous step was 0. So I said that divergence of b at n minus a half was 0. And this is the value of the divergence at the step n plus a half. And I plugged in the evolution equations, and I just got 0. So this is a simple demonstration why this is so efficient. You displace the field components, and it all gives you a divergence of b equals to 0. And the method is very useful because you can easily extend it to basically any grid that you want. You can do it not necessarily on a Cartesian grid. You can do it on a spherical grid. And this is the example of how the e-mesh would be defined on a spherical grid in 3 dimensions. Basically, again, your electric fields would leave in the middle of this cell borders, and the B's would live at the centers of the cell interfaces. The way how would you construct a numerical scheme for this case, you would use integral version of the Maxwell's equations. So you can formulate not in the differential form, you can formulate them in an integral form. And for this, you do this usual things. The equation, which is d dt minus let's start with this minus c curl E. You can integrate this equation over a cell over the cell face, and then you'll get the usual thing that d flux over dt is equal to minus c curl E, the flux of curl E. And this is nothing but a line integral of E along the contour that encompasses this contour over which I computed the flux. So this is the contour. This is L, and S is basically the area of this contour. So you can use this in an integral form. It works in basically any geometry. It doesn't assume anything about whether you live in flat space, you live in curved space. You can formulate these integral theorems basically for any problem you want. And then you just use this content that electric fields and magnetic fields are displaced. You evolve them with the leapfrog method. You get a very accurate second-order algorithm, which conserves div b equals to 0. So that's all very nice properties. So charge conservation is a little bit more tricky, and Lorenzo talked about this a little bit. You can either try to invent a way to conserve current directly, which I will talk about a little bit later, or you can use what's called the parabolic divergence cleaning, which is basically involving solving Poisson equation. And when we're talking about solving Poisson's equation, we're basically saying that the electric field that we got at the end of the evolution time step, where we solved the Maxwell's equation for the electric field with the current, was not that gives you a correct divergence in the charge density. So I'm saying that this corrected electric field or new electric field is whatever the evolution equation gave me, plus a small correction, which I will express as a gradient of the potential. So then I need to solve for this, and the equation for this would be very simple. I just need to plug this back into Poisson, and what I'll get is that the divergence of this gradient delta phi is divergence of E minus 4 pi rho. So this is basically a small quantity, the deviation of the divergence of the electric field that I got at the end of the evolution time step and the actual charge density. We assume that the error that accumulates over one time step or several time step is low. So here you do a little bit of cleaning, and for that you do a Poisson equation. So the divergence of a gradient is a Laplace, and this you can solve where this is basically a known function of the position. It actually, I'm not very sure that this is going to be much slower than the full way of doing the current deposition. And the trick here is that you don't need to do this at every time steps. You can do this at each 10th time step or each 15th time step, and it would still give you very nice results. So the two sort of most known codes on the market, Tristan and Zeltron, they actually use conceptually a different step for the current deposition. Tristan uses charge conservative deposition, and Zeltron uses this Poisson correction. And for problems that we tested, for example, magnetic reconnection, the answer is basically indistinguishable. You can just compute the particle spectra and compare it, and they give you basically identical results. So there are much more sort of crucial parts of the algorithm that gives you sort of convergence of the properties of the particles rather than maintaining this divergence equals to rho thingy. I don't quite know if there is any code that uses hyperbolic divergence cleaning or this Dedner scheme of hyperbolic parabolic cleaning, when you basically try to advect the error at a speed which is greater than the speed of any wave in your system and then keeps damping it. For that, you will need to evolve an additional equation for a scalar field. This, I don't know if there is any sort of community code which does this, but it seems very attractive, so I think we should try that at some point. And if you go to the charge conservative deposition, this is where actually things becomes quite tricky, because the most naive choice that we talked about will not work. So if I just try to deposit the current in the most naive way, which is, as Lorenzo said, charge of one electron times the weight of the particle times the velocity of the particle times the shape function, and sum this over the particles, this particular choice will not satisfy continuity equation for charge density and the current density. So the trick is to construct this quantity in a way that ensures that this equation is satisfied at machine precision. This particular choice fails to do that. So there are multiple ways how to do this, and the most straightforward way is just to say that I know what my charge density is. The charge density is sort of defined unambiguously. This is just a sum of the particles times the shape functions. So this is my charge density that deposits the charge on a cell, and I can just use this definition to compute the current through this equation. And in this way, I would be able to construct a scheme which would be able to do this charge conservative deposition basically for any shape function. So this is what's called the Serkipov charge deposition algorithm. It basically plugs this charge density into this equation and gives the answer for J for any shape function. So in practice, we usually use triangular shape functions or maybe second order shape functions. And for triangular shape functions, it's actually pretty easy to compute this. So for this, I consider when the particle moved over one time step inside one particular cell, so it did not cross any cell boundaries or did not went out of my simulation domain. So assume that the particle started here inside one cell, it ended up somewhere here, and I want to know what currents I need to deposit on the vertices of the cell. So if you if you remember where electric field lives on the cell, you'll remember that they live here. This is your electric field in X. This is your electric field in Y. They live at the borders of the cell, and these are the same positions where I need to compute the current. This is because if I ignore the electromagnetic part, I'm solving something very easy, something like this. d dt equals to minus J. So from this is very clear that I need to define electric field and the current density at the same positions in the cell. So my EX and JX will live at the same places, right here. And I just need to compute the change of the charge density deposited by trajectory of this particle. How would I do this? I would again try to do something like an integral theorem. If I'll just try to compute the change of the overall charge in this volume, this will give me the flux of the current through the appropriate phases. So the change in the charge will give me the flux of the current, which will be something like this. Okay. So this is a flux of Jx through this border. This is a flux of Jy through this size, and this is the change of the charge inside the cell. So this is computed straightforwardly. You just get the change in the shape functions at this position. So you get something like so basically, this is a product of shape functions in x and y direction. They are both linear. These are these triangles that Lorenzo talked about. This is the values for the final position of the particle. This is the values for the initial positions of the particle. So if I'll just take this and rearrange it in a way, I will get this particular answer. So this is the value of the current that I deposit as an x component. And if you compare it from the naive expectation, it's actually pretty close. This fx is just the velocity of the particle. The fx is just the difference between the positions of the particle, and this is the weight which I attribute to this particular point on the cell. And this 1 minus wy is actually nothing like the shape function computed at the midpoint of the particle trajectory. So instead of obtaining something like jx equals to the shape function in the x direction times the shape function in the y direction times the velocity, I got something like jx is the velocity in the x direction times the shape function in the y direction computed at the midpoint of the trajectory. So something which is pretty close to what you would naively expect, but sufficiently different to ensure that this equation is satisfied at the machine precision. So there is nothing sort of conceptually more difficult if you deposit the current in this way or in this way. It's just that one way ensures that the charge is conserved, another one does not. And the problem obviously appears when the particle crosses the cell boundaries, and people came up with sufficiently efficient ways of computing the splitting of the trajectory into two pieces. So if a particle crosses the cells like this, these are 4 individual cells, and the particle went from here to here, what's done now is that you split this trajectory into two pieces. One piece goes from here to the cell edge, and then from the cell edge to the final point of the position, and then you basically treat the two individual trajectories as treated in the previous algorithm. And then if the particle crossed something like this, you can introduce what's called a relay point somewhere in between this on this border of the cell, and again split it into two pieces. So basically, this algorithm allows you to treat any possible way of the motion of the particle through the cell and ensure that the current that you will compute will be deposited in a way that this equation is satisfied. So this is how PIC codes treat this constrained transport of B and electric field in sort of conservative fashion. Any questions here? I think it's good just to show, glory details of how the code works, because my feeling is that, if Charles would tell me how GRMHD works, I would not be able to code it in a week. The PIC code you can code in a week. So if you actually want to do this, it's very simple. This is just something to remind you how the particle pusher works. And here I just want to make a small comment that this is basically what's called a Boris scheme. It also uses a leapfrog update. The velocities are defined at integer time positions, and everything else is defined at time positions in between them. The key here is that the choice of this velocity on the right-hand side is basically arbitrary. So what Boris designed and what Lorenzo described to you the first slide is that you basically split the whole update into 3 pieces. You first do the update with the electric field for half a push, then you do the Boris rotation in the magnetic field, and then you do another half of the electric field update. The choice of this velocity that is given after the first electric field push is basically arbitrary. So it's motivated by the fact that we want an algorithm which conserves energy if no electric field would be present, if the particle just moving in the magnetic field would exactly conserve its energy. But in principle, this is an arbitrary choice. And this results in this definition of the 3 velocity. So there is a continuum of other choices of 3 velocities which would satisfy different properties of the algorithm. And in particular, there are interesting choices which, for example, want to respect Lorentz invariance of the equation. So that would result in a different pusher known as a wave pusher, and that would result in much better qualities of conserving, for example, a motion of the particle moving in crossed electric and magnetic fields. So if you have a particle in electric and magnetic fields and they are perpendicular, what the particle wants to do, it wants to move with the drift velocity perpendicular to both electric and magnetic field. So Boris' algorithm would do a very poor job if this drift will be relativistic. The relativistic drift would be not conserved properly. If you would do a Lorentz invariant algorithm, that would conserve the drift pretty much exactly. And Then there is a third family of choices for this velocity at the midpoint position, which would basically satisfy another property that I would demand, is that if there is electric field, that the energy that the particle actually gets from the electric field is consistent with what you would expect by just computing this analytically. So the particular choice would satisfy something like delta gamma of the particle over time step, which is gamma I plus 1 minus gamma I, would be equal to the work of the electric field done on the particle. So this would define yet another choice for this midpoint position of the three velocity. And this would be different from both the Boris choice and the Way choice. So there is no unique solution for all problems. The Way algorithm is, for example, extensively used in problems of laser plasma interaction where the relativistic drifts are important. The Boris algorithm is heavily used in non-relativistic applications and in relativistic applications where the drifts are not important. So it's still an active area of research of how to construct the most efficient algorithm to do particle pushers, with this particular one just being the most popular. Okay, and before I go to interesting multi-scale applications, I just want to make sure that you guys know how to compute stability of numerical schemes. And for this, I would do two particular simple exercises, one of them being computing numerical dispersion of electromagnetic waves in vacuum with this finite difference time domain scheme. And then we'll compute the numerical dispersion relation for Langmuir waves in a full PIC scheme. Okay, so if I want to propagate electromagnetic wave along one direction in, let's say, x, I need to define one component of the electric field, which for my particular choice, I would say would be EY, which would leave at cell edges. And then I would define the magnetic field in the z direction, which would leave right in between them. So I need to solve two equations, d dt equals to c curl b, and another equation being dB dt equal to minus c curl e. Okay? So this is very, very simple. You discretize it. You say that electric field in y at 3 plus n plus 3 halves I minus ey at the position I at the moment n plus a half is equal to what I will call big C times bz at n plus 1 position I plus half minus bz n plus 1 at the position I minus a half. So again, this is a leapfrog scheme for this equation. You take a time derivative for an electric field which lives here. For that, you need to compute a curl of B at this position. For that, you just take a difference between BZ here and here. This computes a curl of BZ at this position to second order. This is what you get. And then the second pair of equations would be for BZ. So this C is basically the current number, C delta T divided by delta X. Okay? And to know the properties of numerical waves, you just need to plug for each E and B, you need to plug the usual exponents and say that your T is basically Tn plus T0 plus n delta T, and x is x naught plus I delta x. So if you plug this to here, you'll get this dispersion relation, which is quite different from you would expect from your analytical expectation. So analytically, we expect that waves in vacuum propagate at the speed of light, that we'll just get omega equals to ck. This dispersion relation obviously depends on the choice of the time step, the cell size, and the current number. So only in the limit of very small delta t's and delta x's, you can Taylor expand this signs, and you will just get omega delta t divided by k delta x is equal to the current number. And this is a familiar vacuum dispersion relation. So this is omega equals to ck. So in the limit where everything is resolved, of course, we recover the analytical expectation. However, in practice, you get finite time steps and finite grid resolutions, in which case your dispersion relation would look like quite differently. And if I'll try to just picture it, it would look something like this. This is omega, this is k, this is a light cone, omega equals to ck. So at large wavelengths or small k, effectively my wave is sampled with enough grid points. So I would expect that it would look something like this, very nicely following the light cone. And at high k, meaning small wavelengths which are unresolved, my dispersion would deviate from what I would expect. And it would look something like this. So this is basically the shortest wavelengths that I can resolve on my grid, which is just 2 times the value of the cell size. This would correspond to a k equal to 2 pi divided by lambda. This is just pi divided by delta x. And for this particular k, if I plug it in here, the sign would get to 1, and I would get sine of omega delta t divided by 2 is equal to c. So for a code to be stable, this thing needs to be less than 1, because sine has to be less than 1 to return your real solution for omega. So if the current number is less than 1, the solution for this equation would give you a real value for omega. If this is larger than 1, you will get complex solutions, meaning a numerical instability. So you cannot choose your time step to violate the current condition. It will explode in electromagnetic waves, basically. This is well known in all other codes. However, for peak codes, there is this very subtle issue which refers to interaction between waves and the particle. So you know that if the particle is traveling at the phase speed of the wave, there can be a resonant interaction between the wave and the particle. This is known as a Landau mechanism, which could leave both for damping of the wave or excitation of the wave if you have an instability. So this refers to a particular case when the sort of all the waves are properly resolved. So now here, your numerical light, which is electromagnetic wave, which can propagate at a speed which is less than the speed of light. And the equations of motion of particles formally ensure that the maximum speed that they can propagate is the speed of light. So what we can have now is that the particle can propagate at a speed faster than light. So this is well known. It will give you Cherenkov radiation. It is possible in the media where the phase speed of light is less than the speed of light in vacuum, and then you can have the Cherenkov radiation. Here we will get what's called a numerical Cherenkov radiation, because it arises only because we would not be able to properly resolve the speed of our electromagnetic waves. There are multiple ways how you can deal with this. The most simple one, you can just say that this was a second order algorithm. Let's say we go to a more accurate algorithm, let's say a fourth order. The dispersion curve would actually be looking something like this. So all the waves would become effectively superluminal, which would suppress the numerical Cherenkov. but it happens that it doesn't suppress it sort of fully. There are other modes coupling between the particles and the electromagnetic waves, which would still restore the instability. So this is a very subtle issue for modeling relativistic flows. There are no good answer to this, like sort of a well-defined recipe to avoid this completely. There are a lot of recipes which would say that I can run my simulation longer and basically delay the issue. So we can do this. We can filter currents, which would reduce the noise and also help with this problem, and all sort of other tricks which are possible in practice. Okay, any questions here? This is simple, but I think it's nice to go through all of this analytically.
I would just add that to reinforce that this is actually subject of current research.
Yes.
A paper a couple of days ago that actually addressed this exact problem.
Mm-hmm.
It is actually something.
It's something that worries all of us at some point. And then I would touch the last subject, which is the stability of the whole code. So the current condition gives you a stability for propagation of electromagnetic waves. However, we know that in real plasma there is gazillions of all other waves, including the Langmuir waves, and you also need to make sure that they don't blow up numerically. So Langmuir wave is basically a wave which is launched by a locally created charge in neutrality. When you basically enhance the density of the one species, it creates an unbalanced electric field, and the whole plasma starts to oscillate at the plasma frequency. So the one-dimensional system of equations that models it is very simple. Let's say your ions are immobile and electrons are just moving to ensure that the plasma is quasi-neutral. So this is equation of motion for electrons, and the equation of motion for the electric field would be something like this. And this I can discretize in exactly the same way that that the leapfrog is doing. Let's forget about relativity for now and just say that this is the free velocity of the electron. So this is going to be so again, I'm using the electric field at a moment half between the time position of the velocity of the particles, and same for the current. So here I'll skip this point, but in 1D you can actually make sure that the most naive charge conservation is actually exact for triangular shape functions. So if you take a triangular shape function in 1D and just deposit the current in this way, the charge would be exactly conserved. So that issue that I talked about only arises in 2 dimensions. So if I just plug the complex exponent for both velocity and the electric field component, what I'll get is something like this: m times the amplitude of the velocity and for second equation I'll get okay. And they can solve this for the frequency, and the solution would look like again, in the limit of very small time step, the sign can be Taylor expanded into just the argument, and you'll get the omega is plus minus omega plasma. So these are basically Langmuir waves, which are recovered in the limit of the very small time step. And at the finite time steps, you actually encounter a numerical instability if this value is larger than 1. Again, the sign will become larger than 1, meaning that there are complex solutions to frequency, and this brings you an instability. So if this is greater than 1, omega becomes imaginary, and this is an instability. So resolving the plasma frequency in time is basically required to give you numerical stability. And then we get the current condition. And that's pretty much it. If your time step ensures that this and this is satisfied, the code will be stable. You could ask what would happen if your code would not resolve the Debye lengths. The code would be actually stable, so there is no problem in not resolving the Debye lengths. What will happen is just that the plasma will heat up from noise to restore the temperature, to basically increase the temperature in a way that the Debye length becomes resolved. So there is no problem in running this simulation in terms of numerical stability. As Lorenzo described, you would lose physics, which happens on the Debye scale of initial plasma, but sometimes you can live with this. This is not like a big issue of the algorithm itself. However, you do need to make sure that the time step resolves the plasma frequency and properly propagates numerical light. Yes, sorry. So this is for stability. So for stability, that has to be less than 1 and less than 1. And the last note that I want to make is that the code that we described with Lorenzo is actually not conserving everything that we wanted. So the code conserves the total momentum, the momentum of electromagnetic field plus the plasma, but it doesn't conserve the full energy. So this finite difference time domain method for propagating electromagnetic waves ensures that the energy of the electromagnetic waves is conserved in vacuum. So in vacuum, this is conserved. The particle pusher ensures that the energy of the particle which rotates in just the magnetic field is conserved. But that's it. If these problems leaves individually, they're nicely conserved. If they're coupled, the exact energy conservation breaks. And it basically means that you cannot run your code indefinitely because at some point the error in your total energy will become basically comparable to the initial energy. So for typical parameters, this means we can typically run the simulation for 1 million plasma oscillations. Beyond that, typically, it's very hard to run the simulation longer for these choices that we described. The second order algorithm for both particles and fields, the first order shape functions for the deposition of the current, etc. So this is one point where implicit algorithms can be useful. If they resolve all the necessary physics, meaning that you don't take this advantage of taking very large time steps, you take the time steps that properly resolve all the physics, the advantage that the implicit code brings you is that you can conserve the total energy of the plasma on the machine precision. So that's, I would say, the only sort of well-defined advantage of implicit codes compared to the explicit codes. They're much more computationally extensive, so I would think a lot of times before actually trying an implicit calculation.
I guess it's also sort of like fair to say that conserving the total energy does not ensure that the
Yes.
energy
Yes. Yes. In principle, you would want that the evolution conserves infinite amount of momentum of the Vlasov equation, saying that we conserve only one or two, let's say the total momentum and the total energy, it's good to think about this, but it doesn't ensure that the answer that you would get would be totally correct from the physical perspective. So there is no good way out of it, sort of numerically speaking. Any other questions about the algorithm before I would move on to some more interesting things about applications? Okay. So I would move to a particular application of all of these codes, which I particularly like, which are pulsar magnetospheres. If you don't know what the pulsar is a neutron star, basically a 10-kilometer dense object of matter, which happens to have a gigantic magnetic field on its surface. Pulsars have magnetic fields from 10 to the 8 to the 10 to the 12 Gauss. They're very fast rotators. They rotate from periods from few milliseconds up to 1 second. So you basically have a 10-kilometer ball with 10 to the 12 Gauss magnetic field spinning like crazy around its axis. And the question is what this will do. And observationally, we know this will do a lot of exciting stuff. Pulsars has been discovered in radio waves, but they observe through the whole electromagnetic spectrum. They emit X-rays, optical, they emit gamma rays. So we see a lot of electromagnetic radiation coming from this neutron stars. And the basic physics that happens is very simple. You have this neutron star, you spin it in the magnetic field. This is a unipolar inductor that Faraday described to you. So if you spin a magnetic field, you induce electric fields. So this is basically this unipolar induction effect. If you'll measure the potential between here and here, you'll measure a finite voltage. So part of this voltage would point along the magnetic field of the neutron star. So this electric field is so strong that it will basically pull out electrons or even ions from the upper layers of the neutron star. So instead of vacuum around the neutron star, this electric field in vacuum would pull out particles. So these particles now travel along curved magnetic field lines. So they do along this dipolar magnetic field lines. And when a charge moves along a curved magnetic field line, it should radiate, right? Because it experiences an acceleration towards a local center of curvature because the trajectory is curved. So this is what we call curvature radiation. And for pulsar parameters, this is basically ends up in GeV range. So you have a GeV photon propagating in a 10 to the 12 Gauss magnetic field. And what it apparently does, it does the absorption of the GeV quanta in the high magnetic field into electron-positron pair. So you got one charge stripped of the neutron star surface. It emitted a GeV photon. This GeV photon got converted into a pair. These new pairs are now picked up by this electric field that was there. They again accelerate. They again emit this new photons. And this new photon is going to be again absorbed in the strong magnetic field. You get new pairs. So this process basically fills out the surroundings of this neutron star with plasma. This is not a usual plasma that you find in the laboratory. There are very few ions that you could rip off of the neutron star surface. This is mostly pair plasma, so you get electrons and positrons. The densities are, however, very low. So the density that you basically extract out of the neutron star surface is what we call a Goldberg-Julian density. I will explain later what does it mean. But the density for typical parameters is low enough that the collision mean-free path is basically way, way bigger than the system size. So you get this collisionless pair plasma living in a very strong magnetic field of the neutron star. This 10 to the 12 Gauss magnetic field basically ensures that the particles can only move along magnetic field lines. If a particle would have a transverse momentum to the field lines, it would emit synchrotron radiation. You can ask what's the time scale for which this particle would emit a transverse momentum. And for 10 to the 12 Gauss and Lorentz factor of something like 100, the synchrotron loss time is 10 to the minus 14 seconds. So basically, immediately, the particle radiates all of its transverse momentum and just travels along the field lines. So you get this one-dimensional flow of pair plasma along the magnetic field lines, which drives currents and charge densities that should modify the initial magnetic field of the neutron star. So the question of this research is basically to find a self-consistent structure for the surroundings of the neutron star, the magnetosphere, and find out how these neutron stars radiate all this electromagnetic spectrum from radio waves to gamma rays. And why multi-scale is important here? Because the size of the neutron star is 10 kilometers. The size of this region where all of this physics happens, which is very close to the magnetic axis of the dipole, is 100 meters. So you get basically a football stadium sitting on top of this neutron star where there is this exciting fireworks of producing lightnings of electron-positron plasma. And then you have a size of the magnetosphere, which is thousands of kilometers. So you have 1,000 kilometers magnetosphere, 10-kilometer neutron star, 100-meter size of the football stadium that emits this pair discharges. So it's an intrinsically multi-scale problem, which we could somehow address with multiple methods. Yes? This depends on where in the magnetosphere we're talking about. So near the star, basically all the pairs will be created via this process. Very little would be created due to gamma gamma because the density of gamma rays is actually low. So the gamma gamma needs like an optical depth, like a sufficient density of photons near the star to start pair production. This is very inefficient near the star, but in what I will describe later, in current sheets that arise in this magnetospheres, you can actually get a lot of pairs. So the gamma gamma is most important, let's say, further away. Okay, so Goldrich and Julian in '69 wrote this paper, which is by now I think like something like 2,000 citations, and they basically sketched a paradigm how these magnetospheres work. So the current that you extract from this region very close to the magnetic axis, so this is both the magnetic and dipolar axis, this close region which supports field lines which can actually extend to infinity, we call the polar cap, the region of open field lines. So some field lines go to infinity, some close up. And this region where it supports field lines that goes to infinity, we call a polar cap. So this is this 100-meter size football stadium where you get this pair of discharges and all the physics which flies out. So what does it current do? So if you have a current, it basically creates a toroidal magnetic field, right? So this is simple. So this current creates a toroidal magnetic field, which would at some point beyond the star would become comparable in amplitude to the dipolar magnetic field. So at this point, you cannot support basically closed field lines. Field lines open up, and you drive an electromagnetic wind, which basically has toroidally dominated magnetic field. So the magnetic field created by the current decays away as 1 over r. The dipole field scales away as 1 over r cubed. So this field has to dominate at some point. So this is a toroidal field. And then you can remember something which is called the Ferraro theorem in non-relativistic MHD. If you have a rotating object, the conducting plasma basically wants to co-rotate with it in order to support like a rigid rotation. So this rigid rotation of a plasma with a neutron star basically gives you an electric field. This electric field is nothing like a co-rotational electric field. Electric field is just minus rotational velocity of the plasma, which is just omega cross r cross the magnetic field. So this is the electric field that the plasma creates just to support this rigid co-rotation with the star. If you compute the divergence of this electric field, it's non-zero. It's non-zero, and that it's equal to the scalar product of omega dot b divided by 2 pi c. So this is non-zero, and this is what we call a Goldrich-Julian charge. So the plasma around neutron stars and black holes in general, it's not neutral. It's what we call quasi-neutral. It still supports a net charge, but the density of the plasma is much bigger of both electrons and positrons is characteristic density to support the charge. So formally speaking, some sort of an MHD can be still applicable here because the density of the particles is way bigger than the charge. You can forget about this charge as long as there is this charge to support the electric field. So this electric field points in theta direction, further away from the star. This electric field in theta direction cross the toroidal magnetic field gives you a pointing flux. E theta cross B phi gives you an outgoing pointing flux. So this electromagnetic wind keeps an electromagnetic energy away from the neutron star in the form of a pointing flux. You would not see this pointing flux because it's basically a flux of the electromagnetic energy. It's much bigger than the energy flux in the particles. Unless you come up with a way how to dissipate this flux, it would be still electromagnetically dominated all the way to infinity. So the major problem of this research, how these relativistic objects create electromagnetic outflows, is how actually to dissipate these outflows in order to observe the light that comes from all of these compact objects. So you have this pointing flux of an electromagnetic energy coming away from the neutron star, and then you can ask a question of what's the source of this energy? There is only one source of the energy in the problem. There is a rotating neutron star. So as the wind carries the energy away, there should be a way of how the neutron star slows down its rotation. And the way it does this is that this current that flies away along the open field lines, it should actually sort of close itself on the neutron star surface, just to maintain zero current in the system. So to close the current in the magnetosphere, it should cross magnetic field lines right here on the polar cap, and then you'll have current basically going across magnetic field lines. Magnetic field lines are radial. They basically go away from the neutron star. The current flows in theta direction. You get an ampere torque of this current on the neutron star surface that slows down its rotation. So basically, all of the evolution of the pulsar is driven by electrodynamics. The slowing down of the central source is driven by electromagnetic torque on a solid body, and then there is electromagnetic flux which carries energy away from the neutron star. So there is nothing about sort of physics of the neutron star that we don't know, how these objects sort of work from the ground perspective. And then it took surprisingly 40 years just to understand how that simple model that I described works on a quantitative level. And here I would like to get back to a question that has been asked, I think, yesterday about what do we call by force-free electrodynamics in relativistic problems. And what we are basically doing is that we consider the momentum equation of plasma motion, which tells us that the change in the momentum of the fluid is equal to the Lorentz force plus the sort of grad pressure like terms, which concerns with the pressure of the gas. So in this environments of neutron stars, the B field is so strong that the energy density in the electromagnetic field is much, much bigger than the pressure of the plasma. So in these equations, you can basically forget about everything that talks about plasma. You can forget about inertia of the plasma. You can forget about the plasma pressure terms. And what you end up with is a very simple equation. Lorentz force acting on the plasma is equals to 0. So in environments of sun, this just leads to J cross B equals to 0, which means that the current flows exactly along the magnetic fields in the force-free state. In the rotating magnetospheres, as I described, there is electric field and there is a charge density. And if you're actually far away from the source, you try to co-rotate with the neutron star at the speeds comparable to the speed of light, and then the electric field becomes comparable to the magnetic field. So the electric force, which comes into the Lorentz force, cannot be neglected. And the equation starts to look something like this. Okay? So this is a force-free equation for relativistic plasma. It has the electric force, which is just the net charge density times the electric field, plus the Lorentz force, and it all equals to 0. So how we go from here to some equations that can be solved on a computer? So you know that for Maxwell's equations, you need to find the current. So the current can be found from this equation. It's this is basically an advection of the charge density with the E cross B velocity. So as you remember, the charge which is put in an electric field which is perpendicular to the magnetic field wants to do a drift. So this is a drift velocity times the charge density. This is this advection current. And then there has to be some current along the magnetic field, which is unspecified by this equation. If I plug in the current which is along the magnetic field, this is exactly 0. This equation doesn't constrain this parallel current at all. So in order to define this parallel current, we remember about the second condition that the plasma wants to do, which is electric field along the magnetic field equals to 0. So why does it do this? Because if anything, the only thing I know that plasma does, it doesn't like electric fields. So if you put plasma in electric field, one sign of the charge will go one way, the another charge will go the other way, and they will try to create an electric field to balance the external electric field that I put in initially. So if the number of particles is large, there cannot be any electric field along the magnetic field. So this is the most fundamental thing that plasma does. I don't know like if there is a more fundamental thing about the plasma rather than it screens the electric field that you want to put it in. So we have this condition, and in order to ensure that this is true at all times, we need to ensure that the time derivative of this is also 0. Okay? And to find this, I can actually use Maxwell's equations again. So this is something like time derivative of the electric field times B plus time derivative of B dot electric field. This is equals to 0. So this I know is something like a curl B minus J. And this is minus curl of the electric field. Okay? So now you have curl of B dot B minus J dot B, which is exactly the current that I wanted. It's a current along the magnetic field, minus curl E dot E. So if I solve this for the current along the magnetic field, I would get that answer that is on the slide. So this is the parallel current. So now I have my current, which is the advection current plus the current along the magnetic field. It's purely a spatial function of the electromagnetic field. It's the best plasma physics theory possible. It forgot about every plasma effects that are there. There are only electromagnetic fields left. And then we have basically Maxwell's equations, which do time derivative of the electric field equals to curl B minus the current. Current is the function of the electromagnetic field, and dB dt is also the spatial function of the electric field. So all the plasma physics got hidden into this equation for the current, and basically you can use the same electromagnetic method that we described for PIC. You can stagger electric fields and the magnetic fields on the mesh, use the E mesh. This will exactly satisfy div B equals to 0. You don't worry about div E equals to rho because there are no particles deposited on the grid. And then just use this current as a source term for Maxwell's equation. So it looks like a most fascinating plasma physics theory ever. Like very simple, just two equations, just electromagnetic fields, that's it.
How do we know that we're not going to just have a large acceleration of these particles?
Of course, there is no free lunch in this problem. What these problems typically do, if you start to evolve this dynamically, they form current sheets. And this is where this theory breaks. In the most naive way, it breaks because division by zero is a very bad thing to do. So where B field goes to zero, this assumption about the dominance of the electromagnetic field breaks down. When the B field goes to zero, you'll have reconnection, and magnetic field energy will get transformed into plasma. And all these terms going to be important. And in principle, it's a collisionless plasma, of course, so the very first point of using this as a fundamental equation is not very justified. However, if you want to find the global structure of the magnetosphere, just looking into how the electromagnetic fields look like, that's perfectly okay. You can do this, and you need to do dirty tricks to keep the current sheet stable. So the most naive way is just to get the resistivity into the problem. So you can get points where electric field becomes larger than the magnetic field and say there is some resistivity in that region in order to support the current. So this is basically what Anatoly Spitkovsky did in 2006. And what he found is that there are closed field lines, as Goldrich and Julian taught us. There are open field lines. There is toroidal magnetic field on this field line, so this is the color. The current flows exactly along those field lines. It creates a toroidal field. It's different into hemispheres. Beyond this point, which we call a light cylinder, where we cannot no more correlate with the speed of light, these two opposite polarities of the magnetic field touch each other, and this is where the current sheet is created. So this looks very similar to any sort of Earth's magnetosphere interacting with the solar wind problem that some of you may be familiar. You almost always find current sheets in the global magnetosphere. So this is what this thing does. And the current is closed in a very simple way. There is a current going out on opal field lines, and then there is a returning current through this current sheet and the boundary of the separatrix. So this is like a most simple way of how this magnetospheres look like. And the asymptotics of this wind is very nicely defined by the solution which got more attention in the black hole context when basically the same solution in GR is called the Blandford-Znaik monopole. In the case of a neutron star, this is called the Michael monopole. So you basically have radial magnetic field lines. Then you get an equator where the two opposite polarities meet each other. So this is a radial magnetic field. It's basically nothing like B naught times radius of the star divided by r squared. And then there is current on this field lines, current on this field lines. They create toroidal magnetic field. They also meet each other at the equator. There is a discontinuity in both the radial field and the toroidal field. And toroidal exact solution for toroidal field is B naught times r radius of the star divided by r, and there has to be RL somewhere. So RL is C over omega. So this very simple configuration ensures that the force balance is satisfied, and that's basically a stepping stone for any sort of magnetospheric problem in black holes or neutron stars that you can envision. Basically, any electromagnetically dominated wind far away from the source would look something like this. It will be a split monopole with field lines stretching out to infinity, and then creating these current sheets in between. So this is much more simple than the Blandford-Znaik, but you sort of can get an idea of how this looks like. Okay. Why this has been useful is that we actually sort of, for the first time, got an idea of how the global electromagnetic field structure of the neutron star looks like. But then, as the previous question mentioned, it basically ignores everything about the particle acceleration. So there were no electric fields in the problem that could accelerate the particle.
If I would put a particle in this electromagnetic fields, they would do boring E cross B velocity, E cross B motion everywhere except for the current sheet, which would not bring you any acceleration, no the signs of this physics that I talked about, the pair production, the emission of gamma rays. This has been all ignored by this force free equations. So in a sense, what happens is that this magnetosphere self-regulates it in this multi-scale fashion, with basically two important scales being the large-scale magnetospheric structure, which lives on this light cylinder scales, thousands of kilometers for the typical rotations of the neutron stars. And then there is this pair production, which happens in the region where you do get this unscreened electric field, which we ignored in the force-free model. So the thing is that basically any small-scale sort of electric fields can be confined to the plasma skin depth scale in the dense plasma. So this, for a crab pulsar, this is 2 centimeters at the surface. So you get 2 centimeter size scale where you can actually support large scale electric fields, which would accelerate particles and do all that physics. And what happens on this scale will actually ensure how the global magnetosphere would look like, because this is the region that drives these currents and charge densities that modify these field structures on the larger scale, which actually feed back on the small scales by just saying what are the conditions in this acceleration zone where all this pair production physics happens. So it's an intrinsically coupled multi-scale system, and basically without self-consistent solution for the whole global system, it's impossible to tell anything about how this behaves. And this is where peak codes come in, because the peak codes allow you to model collisionless plasma dynamics without approximations about screening of the electric field. It doesn't ignore particle acceleration, emission of the high energy photons. And what you can also do, you can implement all of this particle creation physics into the peak code. You can add the creation of the high energy photons, because you can say that in the most self-consistent fashion, the particle that moves along the magnetic field would radiate synchrotron radiation, right? And in principle, the electromagnetic solver should track this emission as a self-consistent fields on the grid. However, in practice, the frequency of this radiation is something like gamma cube times the relativistic Larmor frequency of the particles. So you typically resolve this with, let's say, a few time steps. And if you have relativistic particles which move with Lorentz factors of tens and higher, this frequency of the synchrotron radiation is way higher than those you can resolve, which are of order of the inverse time step. So this high frequency radiation from relativistic particles is not resolved by a peak code, but you obviously know the answer to this problem, right? You just open Landau and Lifshitz, and you get the drag force, which describes you how much energy the accelerated particle radiates. So this is nothing like basically a generalized synchrotron formula, which defines you how much energy the particle loses if it travels in electromagnetic fields with a velocity v. So it's a purely local formula. You can use the velocity of the particle, you can use electromagnetic field locally, and you can find how much energy the particle will radiate, and you can deposit this energy on the grid as a high energy photon. So now we are modeling not only charged species, we are also modeling photons. They self-consistently propagate on the grid, and then you can do pair production physics with them. For example, if they travel in regions of the strong magnetic field, you can decouple this photon into a pair, or if it finds another high energy photon, let's say a GeV photon found a KeV photon, then it's a very favorable collision. The energy in the center of mass frame is MeV, so this will produce you a pair. So GeV and KeV photons collided, you get a pair. So all this physics can be self-consistently modeled with this multi-species particle and cell code, which consistently includes radiative cooling of the particles and pair creation. And most recently, we also included GR, which I think, given on that time, I will not get into, but you can ask me afterwards. So now we can basically model radiative physics of plasma in a strong gravity with pair production. So this is most relevant physics which happens in strong field environments of neutron stars and black holes. There is, of course, a compromise in doing that. Of course, if you consider a system where this thing is 2 centimeters, this is 10 kilometers, and this is 1,000 kilometers, you cannot fit it in one simulation on a computer. You need to make compromises. And the compromise here is to fit all the scales in one simulation, basically rescaling the parameters of the problem, but still ensuring that the hierarchy of scales is correct. So you have your smallest scale, which is the plasma skin depth, then there is a radius of the star, and then there is a radius of the light cylinder. So the sort of the ratio between them is artificially small, but the largest scale is still the largest scale, and the smallest scale is the smallest scale. So why does it work so sort of nicely here, and why doesn't it work in other problems? Is of course because of the turbulence. So in this problem, there is pretty much no turbulence. The plasma flowing along one-dimensional magnetic field lines is very hard to excite turbulence. You cannot drive any transverse motion of the particles along the magnetic field. The only thing they do, they slide along the magnetic field lines. The only turbulence which you can excite here is actually electrostatic turbulence. You can get Langmuir waves flying around on those field lines. They can do electrostatic turbulence, but it's not important for sort of larger scale magnetosphere. The strongly magnetically confined plasmas is way more simpler in terms of sort of waves it supports, the richness of the turbulence it can excite, etc. So this is the main, most important explanation why this reduced scales still gives you sort of a nice sense of how this looks like. Yes.
Comment on like what we're missing from the first one and the second one, and why there is a sense that tens is okay. That if you want to put more resolution, you want to put it on the radius versus skin depth versus the light cylinder versus
It's hard to tell what would be more interesting. I think putting more on the skin depths could be interesting in a global simulation to resolve the discharge physics. But for now, I think that local simulations is a nice compromise. So you just set up a simulation with local conditions. I'll show one example of that. So local simulations, you can scale for this number to be thousands. So I now run something like 100,000 square simulation where this thing is like 2,000 or something. So there is little change in the behavior of this discharge as you increase this number, as soon as this is something like 50. This is more tricky to sort of check rigorously, because you cannot set up a local problem which would fake the small scale of the neutron star and the light cylinder. But so far, what we've seen trying to increase this, for example, in force-free simulations, there is nothing that kicks in at, say, 10 or 20. So a millisecond pulsar can be, in principle, simulated like sort of directly for this scale, not for the young pulsar, where this ratio is like sort of thousands, but when it's like a few tens, 100, this you can simulate directly. Okay, Lorenzo touched a little bit about a reconnection. So you get this equatorial current sheet. It's again this regime of reconnection when all the energy is in the magnetic field. If you convert all of this energy of the magnetic field into particles, you'll get relativistic energies. So the energy reservoir is the magnetic field, and this magnetic field sort of transferring the energy into the particles through reconnection will give you relativistic energies. However, there is another parameter in this problem which defines you the cooling strengths of the particles that got accelerated. And this particular strong magnetic field, this cooling is so strong that basically it will limit your acceleration. And the parameter that is used to describe this effect is what we call gamma rad. This is basically the Lorentz factor at which this synchrotron loss force becomes comparable to the Lorentz force acting on the particles. So if you balance the Lorentz force with the synchrotron loss, with the synchrotron losses force, you'll get this gamma factor. So this is nothing like sort of charge times electric field. equals to this, which is the losses of energy in terms of synchrotron radiation. You'll get this gamma scales as 1 over square root of b. And this basically defines you as an energy scale at which losses becomes important. And for pulsars, this gamma rad is actually comparable to sigma. So if a particle wants to accelerate to an energy comparable to equipartition, it will have very hard times to accelerate very far beyond that because the synchrotron loss time will be very small. So this energy scales defines you a synchrotron, the energy of the synchrotron photon, which surprisingly doesn't depend on the magnetic field because the energy of the synchrotron photon is b times gamma squared. Gamma squared is 1 over b, b cancels out, and this is a fundamental constant of nature, 1 over alpha, which is the fine structure constant, times the mc squared. If you compute the numbers, this is 160 MeV. So this tells you that a synchrotron photon emitted by a particle in a strong magnetic field cannot be of energy of more than 160 MeV. This is what people call the synchrotron burn-off limit. So I told you that pulsars emit GeV. So how they overcome this problem of the synchrotron burn-off limit. And the trick here is that reconnection creates specific conditions to overcome this problem. And the specific condition is that the particle is accelerated where the B field goes through 0. So what you get here is that, as Lorenzo described to you, the current sheet breaks into a sequence of plasmoids and the regions in between them, which we call X points. So in this X points, the magnetic field is weak. It's basically 0. You have this accelerating electric field, which just pushes particles to high energies as if it is like a sort of an electrostatic electrostatic accelerator. And then these particles get advected into plasmoids where they actually radiate their energy. So this is a particular regime of reconnection which we call radiative reconnection, when the radiation losses actually determine the dynamics of the highest energy particles and of the overall reconnection process. So the particles are typically accelerated in this X points where B field is low. They can easily accelerate to energies which are in excess of this gamma rad limit that I defined. And they can radiate energy, their energy as synchrotron photons in these plasmoids with energy of the photons bigger than this burn-off limit. E burn-off. So this is basically an explanation how particle acceleration and reconnection can avoid this burn-off limit of producing synchrotron photons at 160 MeV. It can radiate all the way to GeV and etc. So another difference with conventional reconnection is that if you convert all of this magnetic field energy into particles and apparently into radiation, because the synchrotron loss time is very slow, very small, you'll create such a density of photons that they will become actually optically thick. So the sheet will radiate the broad spectrum of radiation from X-rays to gamma rays, and at some point pair production will trigger. So you'll get this low energy photons colliding with high energy photons, and they will create pairs. So this pair is going to be sort of mass loading this current sheet self-consistently. And if you'll look at the definition of the magnetization, if you increase the energy of the particles, you decrease sigma, which means you decrease the amount of energy available for particle to acceleration. So it's some sort of, again, a self-consistent machine which loads itself with particles, with this loading sort of defining the scale to which the particles can accelerate. This limits defines you how many photons you can produce, which apparently defines you the energy, the number density of the particles, and it's also sort of self-coupled in the self-consistent fashion. So you cannot ignore basically neither pair production, neither the synchrotron losses in order to study this reconnection. Yeah, this is just a slide which sort of tells you how you can model this magnetospheres. You use this self-consistent particle and cell loop that I talked about, and then you add this extra sort of radiative, which we call extreme plasma astrophysics, sort of radiative effects coupled consistently with these with the collisionless dynamics of the plasma. Okay, and now I'll just show you a couple of movies in the last 5 minutes. So this is how the aligned solution looks like. What's shown is the electron density and the positron density. The white lines are magnetic field lines. I started from vacuum. I started spinning the star. There was basically vacuum electric fields, which were accelerating the particles in the first place. They were accelerated to high energies and started to produce another sign of particles. So the outgoing electrons started to produce positrons, and this is how the magnetosphere started to fill with plasma. So you start to get this dense current region at the boundary of the closed field lines. You get this current sheet, which broke up into plasma instabilities. And then the interesting physics happens here, near this open field line region right here. The zoom-in picture into positrons shows that the production of these charges is very time-dependent. And this is basically a very active area of research, not only in this plasma community, but also plasma astrophysics community, but also in laser plasma interaction, because people now reach intensities of lasers which can actually start to producing pairs in vacuum out of the high energy photons. So what you get here is that this discharge actually happens very in a time-dependent fashion. And the reason is very simple, because once you start producing these particles, they start to kill this electric field, which was accelerating the particles in the first place. So you got, say, one particle, it accelerated, it produced more particles, and now these particles don't like the electric field, right? They want to screen it. Electrons will go one side, positrons will go the other side. They will create electric field in opposite direction to the initial electric field and screen the whole thing. So once the whole thing is screened, the next particle doesn't want to get accelerated because there is no electric field. And you need to wait before this whole cloud sort of escapes, and then you get new particles, a new cycle starts, etc. So this self-consistent plasma simulations are actually for the first time allowing us to address how these plasma flows are intrinsically time-dependent beyond any sort of analytical expectations of earlier models. The whole flow is very time-dependent, and you cannot think of it as just a plasma streaming along the open field lines with some sort of a uniform density. It's fluctuating basically on all scales, and the reconnection in the current sheet, which happens beyond the light cylinder, is also intrinsically time-dependent. And the relevant instabilities here are what Lorenzo mentioned. There is the plasmoid instability, the breaking of the current sheet into these islands and X points, and then there is a relevant instability, which is a drift kink instability, which is when you have this current sheet, it wants to create oscillations in a perpendicular direction to the current. So it starts wiggling around its sort of mean direction. And in 3D, you would actually see both instabilities. This is the plasma density in the frame which corrotates with the pulsar. So the pulsar rotates, and I want to sit in a frame which corrotates with it. You would expect to see a mostly time-independent solution in that frame. And that's what you actually see. The field lines are basically time-independent, unless you're looking at this particular field line, which was just about to reconnect. And then you see it basically reconnecting away and basically transiting from a closed to open field line. So there is this non-steady reconnection, which creates this bubbles of plasma density that you see as the volume rendering here. And this is basically what energizes the particles. Yes?
Yeah, so there's a clear period in the plasma density.
This one?
Yeah.
Yes.
So what sets that?
This is just this physics that I talked about, the period of how fast you screen the electric field in the polar cap region. So basically, this is the intermittency between them sets the height of the gap at which you need to accelerate the particle in order to start produce new particles. So for a typical pulsar condition, this is like a microsecond time scale. So a microsecond will last before the next cloud, before the previous cloud will get evacuated, and we will restore this electric fields to start new pair creation episode. This is sort of like a very small microsecond thing which regulates this discharge behavior. Seems to be what? Yes. So this particular simulation was with low mean free pass of photons that are produced in the current sheet. So basically all the photons that could start to produce new particles, they were localized to the current sheet. They could not travel far away before they would start producing particles. So in the simulations where this mean free pass is larger, we typically see that there is some low density plasma in this cavity region, just enough to screen the electric field. Oh, right, yes, yes. So this is a very, very peculiar thing that, like on the first slide, I described to you that, electrons will get out, they will accelerate, they will produce particles, and that's it. It turns out that if electrons are sort of pulled out, it's not necessarily that they will get accelerated. And the reason for that is very simple, because what I just told you here is that this amount of particles is basically sufficient to screen the electric field. And it's not a big number density. It's just enough to extract from the neutron star atmosphere. So it turns out that there is a second parameter in the problem, which is the large-scale current that you create in this magnetosphere. So basically the large-scale structure defines you what the current should be along this open field lines region, flying from the neutron star all the way beyond the light cylinder. And this current has to be conserved along field lines. This is like a simple thing in a magnetic field line tube. The current along the magnetic field has to be conserved. So this current can be actually anything with regards to this C times this Goldreich-Julian time charge density. It can be either larger, it can be equal, or it can be less. And this, in a relativistic language, this would mean that this current is time-like. The square of the forecurrent is, depending on what you assume for the signature of the metric, I call this less than 0, meaning that this is time-like current, that there is a frame in which there is no current, but there is just a charge density. And this current is space-like, meaning that there is a frame in which there is no charge density, but there is a current. So these two regimes lead to completely different results for particle acceleration. And you can easily guess this. If the current is less than the charge density times the speed of light, you can have this charge density flying at a speed which is current density divided by the speed of light, which is less than c in this case. The j divided by rho Goldreich-Julian is less than c. And this will be my characteristic velocity of the particles. So you basically extract electrons enough to screen the electric field and support the current flow. And it's perfectly enough to fly outwards. And it turns out that a lot of field lines in a semi-aligned pulsar support this electron outflow. So you get basically non-relativistic electrons streaming to infinity without doing all of this fireworks that I introduced initially. And this was also sort of an unexpected result based on earlier analytical models. And sort of the most recent analytical models, of course, found this effect. But like earlier research in the 60s and 80s completely ignored that. And you needed numerical simulations basically to find out what's the self-consistent current flow in this magnetospheres look like. And so you have here only electrons, and this field lines have both electrons and positrons. Okay, it's negative time now, and I'll just show one movie, which is basically why all of this research is relevant, because now we can just compute gamma rays. We can just go over all of these photons that we created in the simulation and plot the light curve. So this is emission of synchrotron photons basically in all directions. So this basically highlights the shape of the current sheet. Particles in the current sheet get accelerated by reconnection. They emit synchrotron photons, and that's what you see as this gray color. And then there is this colored thing, which is the emission which is produced beaming towards you as an observer. So twice per period, you see this two-peak light curve. produced basically by part of this current sheet which travels towards you. And this is very reminiscent of gamma ray observations of pulsars by Fermi. So they typically observe a double peak light curve with peaks separated by something like a half a period. And this is very nicely reproduced in this current sheet model when the reconnection energizes particles and they produce gamma rays that you can see. So basically, some sort of this radiative plasma physics simulations with pair production now allow to predict gamma ray, and in future they will also lead us to understand the radio emission from pulsars. And that's why it's so exciting that we can model sort of self-consistent physics with as many physics ingredients as we like. And particle and cell technique is particularly useful in this sense because it's so easy to add new physics and new ingredients to the problem. The algorithms are very flexible. You can formulate them in curved space-time. You can solve like particle equation of motion in curved space-time. You can add pair production, radiation, all of this. So I think I'll stop here and take questions. Thank you. Sure.
When you were talking about the synchrotron burn-off limit,
Mm-hmm.
and you said it doesn't depend on B field,
Mm-hmm.
but I don't understand something, because then you said that something about in the reconnection where the B field gets very small, this is favorable.
Right. So this model assumes that you emit and accelerate at the same spatial position. So if you accelerate and emit at the same position, this is basically the same magnetic field, right? So in order to balance losses and acceleration, in the same magnetic field, this is what you end up with. And if you consider the energy of the photon that emitted at the same spatial location, you get this. So now in reconnection, you get a slightly different picture. You accelerate in the regions of low B field. So your particles don't know anything about this gamma red limit, which is defined basically with respect to the magnetic field in the upstream of the current sheet. So it doesn't know anything about that field in this place. It gets kicked up by the electric field. It accelerates to high energies. And then as the tension sort of advects the particle into the plasmoid, immediately it starts to feel perpendicular magnetic field. And this is where it radiates. But in that formula, for the photon energy, the gamma is no longer gamma red. It's much bigger. And it's given more like by this magnetization parameter rather than by the strength of the cooling. So reconnection is a very efficient way of avoiding this burn-off limit problem, because you basically break the assumption of how this formula was derived, that acceleration and emission happens at the same spatial location. It's not true for reconnection. Yep.
Is there a reason that you consider acceleration by the electric field here rather than like Fermi acceleration?
So in this particular regime where the losses are very, very strong, it's actually hard to do anything with particles inside the plasmoid, because here they became relativistic in the X point. Then they would end up in plasmoids. They would radiate all of their energy as synchrotron radiation, and they're again non-relativistic particles. Fermi is very efficient if you feed it with something pre-energized. Like this particle that Lorenzo showed in his simulation, it was first kicked up by the electric field in the X point, and then got reprocessed by the Fermi scattering and contracting islands. This first ingredient is killed in this regime, because the particle that ended up in the plasmoid had to radiate all of its energy as synchrotron. So in simulations, we typically see that all high energy particles are concentrated in this X point, and there's very little of high energy particles left in the plasmoids because of the strong radiation force. So that's the main reason why we don't consider like this further steps of energization. Okay, if any more questions, let's take lunch.